Imagine unlocking a monumental leap in how gradients are calculated for machine learning and scientific computing. A breakthrough so powerful it could reshape the landscape of computational science. But here's where it gets controversial. While automatic differentiation is now central to these fields, existing tools are often plagued by restrictions such as demanding tedious code changes, falling short on performance for massive scientific workloads, and consuming excessive memory. These issues frequently force researchers to resort to manually deriving gradients, which can be tedious and error-prone. Enter DaCe AD, a revolutionary system developed by Afif Bouraoud, Alexandru Kalatoiu, Marcin Copec, and Torsten Heffler from ETH Zurich that overcomes these limitations with an ingenious algorithm, delivering staggering performance improvements, sometimes over 92 times faster on common benchmarks, without requiring any changes to the original code. This innovation promises to be a game-changer across a variety of computational domains. Let's dig into what makes this advancement so powerful. When it comes to automatic differentiation, AD, the technique involves calculating gradients of complex functions, a core step in training machine learning models and simulating scientific phenomena like weather patterns or climate scenarios. Scaling AD efficiently for large scientific models has been a persistent challenge. Traditional solutions often demand rewriting code or offer limited support for diverse programming languages, which hinders adoption. The ETH Zurich team tackled these obstacles head-on by exploring memory-saving strategies like checkpointing and rematerialization, which cleverly trade off between saving intermediate results and recomputing them to avoid excessive memory use. They didn't stop there. They devised a memory-efficient algorithm that also exploits modern hardware capabilities, including GPUs and multi-core CPUs, fully harnessing their parallelism. Using advanced compiler techniques, the team automated and optimized AD through source-to-source transformations, making the entire process seamless for developers. Unlike many existing systems confined to specific languages or requiring labor-intensive code rewrites, DaCe AD stands out by working directly on code written in popular languages and frameworks, such as Python, PyTorch, ONNX, and even Fortran. The innovation hinges on a smart balancing act, an integer linear programming ILP-based checkpointing method that intelligently decides which intermediate values to store and which to recompute. This optimization maximizes performance within given memory limits, alleviating the typical trade-off problems faced by scientists. One of DaCe AD's strengths comes from leveraging DaCe's stateful data flow multigraph, SDFG intermediate representation, which meticulously tracks data movements and enables in-depth data flow analysis, critical for efficient gradient computations. By incorporating critical computation subgraphs directly into these SDFGs, DaCe AD elegantly manages both forward and backward computations, even across sequential and parallel loops. The results are nothing short of extraordinary. When tested against JAX, currently one of the leading AD frameworks, DaCe AD achieved an average speed increase of 92 times on the NP Bench Suite, a standard benchmark collection for high-performance scientific computing. To put this in perspective, some specific benchmarks recorded speedups as high as 2,700 times. Even the geometric mean performance, a more conservative overall measure, showed a solid 4.1 times improvement. This showcases the framework's consistent and broad-ranging effect. But let's pause to consider the controversial implications. Does this suggest that current popular AD tools like JAX are fundamentally limited or even outdated for scientific computing? What does it mean for those deeply invested in existing technologies? Could it disrupt established workflows or require a shift in the developer mindset? These questions are worth debating. Underneath these striking achievements lies the core of DaCe AD's architecture. The ILP-based checkpointing strategy, which automatically optimizes memory use by deciding intelligently at runtime which data to keep and which to recompute. This ability to automatically tune checkpointing according to memory constraints is a critical breakthrough, allowing the system to scale efficiently. Furthermore, the use of the data-centric SDFG intermediate representation enables precise management of data overwrites, efficient gradient propagation through complex control flows, and ultimately, a better balance between memory consumption and computational speed. To sum up, DaCe AD does not just provide incremental improvements. It revolutionizes how automatic differentiation can be integrated into complex scientific and machine learning workflows without demanding any code modifications, supporting multiple programming ecosystems seamlessly. The potential applications extend beyond pure scientific computing, hinting at exciting hybrid applications in AI-augmented scientific discovery, AI for science, a direction ripe for future exploration. So, what do you think? Are frameworks like DaCe AD signaling a new era where performance and usability meet without compromise? Or will entrenched technologies hold on despite their limitations? How ready is the research community to embrace such disruptive innovations? Share your thoughts and join the conversation below.